So now we're going to look at some of the data on climate and answer three questions. What has the Earth's climate been in the past? Not just the recent past where we have the most information, but many, many, many thousands of years ago. What is the evidence that climate change is occurring now? So we'll look at the data on that. And what is the evidence that the causes of climate change are anthropogenic? So first we'll look at the first two questions. What has the Earth's climate been in the past? And what is the evidence that climate change is occurring now? So let's first take a look at this graph. You can see this is a graph starting from present day, moving back 50,000 years ago, 100,000 years ago, all the way back to 400,000 years ago. So over a long period of time. And you can see that on the y-axis we have a change to average temperature in degrees C. So warmer is up here, colder is down here, compared from the present day temperature. So take the present day temperature. If it's increased, the number would go up. If it's below the present day's temperatures, we would go down. So as you can see, there appears to be a cyclical pattern here. So there was a peak, some valleys, a peak, some valleys, a peak, smaller peak, great peak, smaller peaks, and then up here to the next peak. So how do we get temperature data from 50,000 years ago, much less 400,000 years ago? Well, there are three main ways. The first is ice cores. So let me show you what it would look like on the next picture, and then we'll come back. Whoops. Okay, so ice cores are cores that are dug into glaciers or other ice formations. And what happens during their formation over thousands of years is that the snow comes down, and in it has trapped air bubbles. And then it starts to freeze as more snow comes down on top and packs that underneath snow down. It turns to ice. The next layer of snow also would have air bubbles trapped in it, and so forth, and that will continue until you get, as you go deeper and deeper into that ice column, you would get older and older air, and a slice can be taken, melted, and the gases in there can be directly measured. So that's one way. Second way is ocean sediments. There is a genus of organisms known as Foraminifera, and they have been around for hundreds of thousands of years. And they're kind of like the roaches of the oceans. They're numerous. They have hard shells that when the organism dies, it lands on the bottom of the seafloor and piles up. And when they look at those ocean sediments, they can again do a coring, a sample, and see which specific species within that genus are present over years. And since those species are still around today, we know what climates different species prefer. So if you have species A that prefers to live in tropical regions, then that would indicate that temperature would be in the tropical range. If you have a different species of Foraminifera and they prefer mid-Atlantic type temperatures, temperate temperatures, or even cold, because these species can be found in very cold climates as well, then you know approximately how how the temperature was when those organisms existed or lived there. The next way is to look at biological and physical measurements. One way is with leaf shapes. So leaf shapes change depending on temperature. If you have a very cold climate, such as in, let's say, Canada's boreal forest, you get a predomination of trees that are coniferous, that is cone-bearing, and have sharp little needles rather than big floppy leaves. As you get down to temperate climates, you have a mixture of trees like we have here, oaks and maples and so forth, with some shape to the leaf and a certain size to the leaf. And then if you go down to tropical and subtropical regions, you find plants with very large lobed leaf shapes. So some of these leaves over the centuries, over the thousands of years actually, became fossilized. And so scientists can go back and look at the age of the fossil and what type of leaf shape was present and determine what the temperature was at that point in time. Now, since 1880, we have been able to take direct measurements of temperature, and that has happened throughout the world, so we'll talk about that on a later slide. Okay, so how do we know, or why did the Earth go through these periods of peaks and valleys with the temperature? Why wasn't it constantly the same? So the reasons are complex. One is that Earth's orbit experiences changes on a regular basis, and the other is that solar output sometimes changes over time. So I'm going to provide an explanation of that. This is not a need to know, this is background information. Okay, it's a big heavy slide, so bear with me. So first we'll look at the changes to the Earth's orbit, because we have a sense already that the ice ages came and went cyclically. So the first is called eccentricity, and that's that the Earth circles the sun in a flat plane. And the explanation of that is the spinning Earth is also rolling around the edge of a giant flat plate with the sun in the center. But the shape of Earth's orbit changes from nearly a perfect circle to an oval shape on a 100,000-year cycle. The second is obliquity, and the Earth is tilted on its axis, and the angle of the tilt can vary slightly, between 22 and 24 degrees, and this occurs every 41,000 years. The next is precession. The axis wobbles toward and away from the sun over a span of 19,000 to 23,000 years. And a mathematician named Milankovitch put together all of these orbital variations, and from that he was able to map out when the ice ages would peak. And he found that ice ages would peak every 100,000 years and 41,000 years, with a few additional blips every 19 to 23,000 years. And in fact, the paleoclimate record shows peaks at exactly those intervals. Ocean cores also show that the Earth passed through regular ice cycles, not just the 3 or 4 that we have recorded on land by boulders and so forth, and glacial deposits, but 10 in the last million years, or around 100 in the last 2.5 million years. I'd like to go back for 1 second, because what I did not include here is that any one of these methods of determining Earth's past climate in and of themselves would not hold much value. But what happens is that when you combine ice cores and ocean sediments and biological and physical measurements, they all overlap and produce a graph that's just the same. And that's where the strength in the data lies, in the number of different methods that have been applied and how they come up with the same result. Okay, so that was Earth's orbit. Okay, I slide slightly out of order. So I do want to mention here, and I believe it appears in a later slide, that the sun's solar output has actually been lower in recent times. So that is not a natural cause to these changes that are currently occurring. So on the next set of slides, we will look at current changes and versus historical changes. So first, let's look at global temperature changes since 1880, when temperature was first being able to be measured throughout the world. So here's 1880 down here and all the way up through 2010. And there's an annual average shown in purple and a 5-year running average shown in blue. You can see there's a general trend upward from 1890 to today. Since 1880, the temperatures have risen about 0.8 degrees C. And this, in fact, is occurring when solar radiation has slightly decreased. Air temperature increases and seawater temperature increases are not exactly the same. So the increase to today in degrees Fahrenheit of air temperatures is now up to 1.9 degrees Fahrenheit. It's actually higher at sea surface levels, being over 2.3 to the 2.5 degree range at this point in time. So you can see on this graph that surface temperatures around the world are not equally increasing at the same rate. So the orange and red here represent higher temperature changes, and the yellow medium temperature changes, and the blue is actually a decrease in temperature changes. So oddly enough, and for reasons scientists don't understand, the North Pole regions and the Northern Hemisphere regions are warming faster than the middle regions and certainly further to the south. So when we continue on to the human causes of climate change, we have to consider the relationship between CO2 and temperature. I'm actually going to stop it here and we'll continue on with another screencast.